Welcome to the deep dive. Today, we're plunging into a concept that, well, it might just fundamentally reshape everything we thought we knew about the universe's most basic building blocks.
Yeah, it's quite something.
What if particles like, the electrons buzzing around your atoms or the photons lighting up your screen, what if they aren't the distinct fundamental entities we've always been taught? What if the very distinction between matter and force? What if it isn't as fundamental as our textbooks make it seem? Maybe more like two sides of a much deeper hidden reality.
It's a truly tantalizing question, right? Because it challenges the very bedrock of modern physics.
Right.
We've become so accustomed to thinking of bosons as, unique force carriers.
Right.
And fermions as separate matter particles, each with their own sort of immutable identity.
Exactly. We box them up.
But what if that's just a surface level distinction, a convenient classification for what we observe, rather than an underlying truth about their fundamental origin?
Exactly. And that's precisely what we're going to unpack in today's deep dive. Our current understanding, it's incredibly successful in describing the universe, right?
Absolutely. Operationally, it's fantastic.
But it might just be a highly effective map of the surface, kind of hiding an even more profound landscape beneath. And that deeper landscape is what Philip Lillian explores in this revolutionary new paper, Dimensional Reduction of Bosons into Fermions, a coherence-theoretic reinterpretation of particle ontology. This work doesn't just tweak quantum field theory. It proposes a truly unified view where particles aren't just distinct entities, but actually emergent phenomena arising from, a deeper, more profound substrate.
Yeah, what's fascinating here is that Lillian suggests that what we perceive as separate particles are in fact just different expressions or maybe states of an underlying coherent reality.
Coherent reality.
It's a fundamental shift in perspective,
Yeah.
It hints at a universe far more interconnected and harmonious than we currently imagine.
Okay, so our mission today is to guide you through this incredibly complex reinterpretation. We'll get into its core concepts, explore the fascinating mathematical operators that describe these transformations.
The how it happens, essentially.
Exactly, the how, and reveal the startling implications it has for, the standard model, for supersymmetry, and really for our entire understanding of reality. By the end of this deep dive, hopefully, you'll have a significantly expanded understanding of what might just be the cutting edge of theoretical physics.
Yeah, we'll introduce you to this idea of a coherence field, which is proposed as the ultimate source of everything.
The ultimate source.
Then we'll explore how concepts like dimensional reduction and torsional chirality locking can literally transform one type of particle into another.
Wow.
It's a single, pretty elegant framework that offers a potential explanation for everything from a particle's mass to the mysterious phenomenon of quantum entanglement.
Okay, let's begin our journey there. Let's set the stage for this new reality. What does Lillian propose as the true foundation of existence? Setting the stage. The coherence field. A new reality. So, let's start with the prevailing view in physics, the one most of us are familiar with, right?
The standard picture.
Yeah, the standard picture. In standard physics, bosons and fermions are considered fundamentally different. Bosons like photons, they're force carriers, integer spin, and they can happily occupy the same quantum state. Lots of photons in a laser beam, for example.
Bose-Einstein statistics, yeah.
Right. Fermions, on the other hand, they're the matter particles, like electrons, half integer spin, and they famously obey the Pauli exclusion principle.
No two alike in the same spot.
Exactly. Meaning no two identical fermions can occupy the same quantum state simultaneously. This distinction, it's absolutely crucial to how we've built the standard model and really how we understand the very stability of matter around us.
That's right. And this distinction, while incredibly successful operationally, it allows us to describe and build everything from lasers to microchips. Lillian's paper suggests it might actually be obscuring a deeper truth.
Obscuring it.
Yeah, it's an effective way to describe what we observe, sure. But if we dig deeper into the origin of particles rather than just their observed behavior, we might find that the division isn't so sharp. The paper suggests it's merely a surface-level quantization rather than an underlying unity. It implies that our current categories might be useful descriptions, maybe approximations, but not the ultimate truth of what these particles are.
So if this fundamental distinction isn't truly fundamental, what is? This is where the paper introduces its really foundational concept, the coherence field.
Yeah, the core idea.
It's described as the underlying ontological substrate from which all particles and forces arise. And it's characterized by structured resonant phase integrity. Okay, that sounds incredibly abstract. Can you help us wrap our minds around what this coherence field actually is?
Absolutely. And we do have to kind of recalibrate our intuition here, maybe even challenge it a bit. The coherence field isn't like the quantum vacuum, which is often pictured as this, chaotic sea of fluctuating virtual particles.
Right, popping in and out of existence.
Exactly. And it's certainly not a return to the old discredited idea of physical ether, some medium that light travels through.
Okay, so what is it then?
Instead, it's defined as a non-local resonant continuum characterized by perfect coherence. Now, this is crucial. Perfect coherence implies the highest possible phase symmetry, completely free from decoherence or any form of discretization. What does that mean intuitively, though?
Yes, what does perfect coherence and phase symmetry truly imply in this context? That's still pretty abstract.
Think of maybe a vast, perfectly still ocean, absolutely tranquil, where every potential ripple and wave is perfectly aligned in absolute sync without any chaotic movement or static.
Perfectly synchronized potential.
Exactly. This phase symmetry means there are no preferred directions or localized disturbances. Everything is perfectly balanced and continuous. And no discretization means no separate individual bits or chunks within it. It's the ultimate state of pure, undivided potential. All possibilities exist as, resonant modes within this field, but they haven't yet taken on specific forms or identities.
So particles aren't just there from the beginning.
Right. Particles in this framework aren't fundamental pre-existing entities that just are. Instead, they are localized expressions of coherence modulation.
Okay, localized expressions, modulation. So it's not empty space and it's not full of stuff. It's pure potentiality, pure resonance, where everything is perfectly aligned and harmonious. And from this field, particles emerge. How does that emergence happen? Is it just random, like bubbles forming in boiling water?
No, not at all. Emergence occurs through a highly ordered process called coherence reduction.
Coherence reduction.
Think of it as a local breaking of the field's perfect symmetry and continuity. But this reduction isn't arbitrary. Lillian states it follows precise topological pathways, leading to the structured modulations we recognize as particles and their specific properties.
Topological pathways, like preset routes.
Kind of. It's like folding a single, perfectly smooth piece of paper in specific, intricate ways to create a particular origami shape.
Oh, okay.
The layer is the universal coherence field, right? And the specific folds and creases are the reductions that give rise to distinct structures, like an electron or a photon.
That's a powerful analogy. It implies that what we see as distinct particles are just different ways the underlying coherence field is expressing itself by locally reducing its own perfect symmetry. It's like the universe is playing different notes on the same grand instrument. Bosons and fermions, two sides of the same coherence coin. So if the coherence field is the origin, how do our familiar bosons and fermions fit into this picture? Let's start with bosons, the force carriers. The paper states that in the highest symmetry phase of this coherence field, bosons are the first to emerge.
The first expressions.
Yeah. They are described as wave-like resonances that maintain coherence over extended domains, with their integer spin reflecting the harmonic completeness of their oscillatory modes. What does this reinterpretation mean for their role in the universe? How does it change how we think about them?
Well, what's really fascinating here is a reinterpretation of their behavior. The reason bosons don't obey exclusion principles, the reason multiple photons can occupy the same quantum state, like in a laser, is precisely because, in this view, they do not break coherence, they extend it.
Ah, they extend coherence.
Exactly. They are literally messengers of this underlying coherence, propagating it across space. So in this model, bosons don't carry force in the mechanical sense we often imagine, like one particle pushing or pulling another.
Not like little billiard balls hitting each other.
Right. Instead, they propagate coherence and distribute symmetry, functioning as what Lillian calls phase structuring agents. They ensure the continuity of resonance fields, acting as the universe's internal communication network, basically maintaining the underlying harmony.
So a photon isn't just a tiny energy packet moving through space. It's more like a ripple in this coherence field, maintaining and distributing its phase structure, like a perfectly synchronized wave in that cosmic ocean you described earlier.
Exactly. And each specific boson type corresponds to a specific symmetry group, which manifests as a particular resonance structure upon this coherence field.
Okay, can you give examples?
Sure. For example, photons are described as modulations of U1 coherent symmetry. That's a relatively simple single parameter symmetry associated with phase rotation. Think of a perfect circle. This explains why electromagnetism is carried by photons. They are the purest expression of propagating coherence.
Makes sense. What about others?
Then you have the WNZ bosons, which mediate the weak force. They appear via SU2, torsional reductions. SU2 represents a more complex internal rotational symmetry, which leads to the short-range nature and the chirality, the handedness of the weak force.
Okay, SU2 is more complex.
And then gluons, the carriers of the strong force, they're redefined as routing SU3, coherence, across what we know as color-charged topologies. SU3 is an even more intricate symmetry group, reflecting the strong, complex binding of quarks. It's all about how the coherence field is structured and distributed at different levels of complexity and symmetry.
That's incredibly elegant, actually, tying particle types directly to symmetries of this underlying field. So, okay, if bosons are these extended coherence waves propagating symmetry and resonance, what happens when that wave gets, well, you said earlier, tied in a knot, or undergoes a dual reduction? How does pure energy condense into something as distinct and seemingly solid as matter?
Right, that's our transition to fermions, the particles that make up matter. According to the paper, they arise from local disruptions of coherence continuity.
Disruptions.
They're described as phase-lock structures resulting from a dual reduction of a bosonic coherence wave. This is a critical point. They aren't separate, fundamentally distinct entities, but derived or maybe transformed from the very same coherence substrate as bosons.
Derived from bosons, okay.
Yeah.
And these disruptions, these knots, they lead to the distinct properties we associate with fermions, right? Like their half-integer spin, the Pauli exclusion principle, and perhaps most radically, their mass. So instead of a particle having mass, it sort of becomes mass, like nodding energy into existence.
Exactly that. The fundamental insight here is this. Mass isn't something a particle is born with, but something it acquires by trapping its own energy.
Wow.
Imagine a flexible, perfectly smooth rope, right, which represents pure, massless energy, a bosonic wave. Now tie a knot in that rope.
Okay.
That knot itself, that act of localized containment, is mass. The more complex or tightly woven the knot, the more mass it effectively has. This revolutionary idea transforms mass from just a static attribute into a dynamic outcome of a fundamental process. The paper states it quite directly. Mass itself is not a property, but a byproduct of trapped coherence.
That is a mind-bending idea. We usually think of mass as this intrinsic property, something a particle simply has. EMC core links mass and energy, but here mass is trapped energy structure. So how is mass literally a function of coherence entrapment?
Okay, let's connect this to the bigger picture. Imagine that perfectly smooth, continuous wave again. It has no localization. It can spread infinitely. This is analogous to a massless boson, like a photon.
Right, goes forever.
But if you then constrain that wave, fold it, twist it, and lock its phase into a specific, localized topological structure, what Lillian calls a coherence knot, that act of localization, of containing and structuring the coherence, requires energy to maintain its form.
Ah, the structure takes energy.
Exactly.
Yeah.
That concentrated, trapped coherence manifests as mass. It's not just a property. It's the energy associated with maintaining that localized constrained resonance. And the deeper the coherence reduction, the more tightly trapped the coherence, and therefore the more mass the resulting structure has.
Because that could explain.
And this naturally explains the mass hierarchy observed in particles, right? From the very light neutrinos to the much heavier top quarks. They're all seen as just varying degrees of coherence entrapment, different complexities of these knots.
So, the electron isn't born with mass. It acquires it by becoming a localized knot of coherence, formed from what was originally a more extended, massless bosonic wave. That's a truly profound conceptual leap. It transforms our understanding of mass from, a static attribute to a dynamic consequence of a topological transformation. 3. The mechanics of transformation. Operators in action. This sounds like a profound transformation, okay, but how does it actually happen? The paper introduces specific mathematical operators that govern this process, acting like, as you said, cosmic origami instructions. Let's get into the mechanics. The first step involves what's called the dimensional reduction operator, or BROAD. Tell us about that one.
Okay, the dimensional reduction operator, RARD. It's the initial key to this whole transformation. It essentially contracts the extended coherence structure of the boson into a lower dimensional phase manifold.
Contracts it, lower dimensional.
Yeah. Instead of getting bogged down in the full mathematical notation,
Right.
like Ebrick becoming Guag, let's focus on what those symbols mean conceptually. The ebb simply describes our initial extended bosonic field, like that wave spreading out across all dimensions of space-time, right? The ARD operator then takes that wave and transforms it into in. This represents a new sort of squished down phase sheet. The ebb signifies that its spatial freedom has been significantly reduced. It's as if a multi-dimensional wave has been confined to a flatter, maybe two-dimensional surface, or perhaps even a one-dimensional line.
So it's like taking, I don't know, a big sprawling three-dimensional wave and squishing it down onto maybe a 2D surface, concentrating its energy.
Precisely. The paper provides a great geometric analogy for this.
Yeah.
Imagine a spherical wave collapsing onto a toroidal surface, or maybe a 2D phase disk, like a deflating balloon collapsing onto itself, maybe.
Okay, I can visualize that.
This process removes certain spatial symmetries and localizes the coherence. It's a concentration of the field. And here's a really crucial insight the paper makes. This reduction is not a loss of energy, but a loss of symmetric extension, a concentration of coherence.
Not losing energy, just rearranging it.
Exactly. The energy is preserved, but its spatial distribution and its degrees of freedom change dramatically. This phase sheet becomes the intermediate substrate, a partially constrained form ready for the next transformation. It's still continuous, but it's now a flattened potential, kind of primed for folding.
Okay, so we've got this squished down phase sheet. It's concentrated, but not yet a distinct particle with properties like spin or charge. What's the next step to truly turn it into a fermion, into matter?
That's where the second crucial operator comes in, the torsional chirality operator, teach.
Torsional chirality. Sounds complex.
It is. This operator acts upon that dimensionally reduced phase sheet, causing it to fold, twist, and lock its internal phase into a topological structure with chirality and spin properties. This is really the point of no return for the wave-like state. It's a truly radical transformation of its geometry, its topology.
Folding, twisting, locking. And what specific outcomes does this torsional locking impose? This is where the fermion really takes on its identity, right? That half-integer spin, the exclusion principle, even charge. How does a simple twist create all these fundamental properties?
Exactly. This is where the core properties of fermions emerge directly from pure geometry and topology. This torsional locking directly leads to.
Okay.
First, half-integer spin. This arises from geometric phase rotation constraints within the twisted structure itself. Instead of a full harmonic 360-degree rotation that returns to its original state like a simple wave, this twisted knot only fully aligns after two full 360-degree rotations, 720 degrees. That gives you the characteristic spin.
Like a Möbius strip. You have to go around twice.
Exactly like a Möbius strip. That's a perfect analogy. Then, exclusion behavior. This comes from its self-referential chirality. Because it's a specific, handed, self-locked knot, identical structures cannot perfectly overlap in the same state. There's an inherent spatial occupancy just due to its internal structure, which explains the Pauli exclusion principle naturally.
Okay, so the shape itself prevents overlap.
Precisely. Then mass. This is the coherence localization energy we talked about earlier.
Yeah.
The energy required to maintain this locked, twisted, and inherently stable form manifests as mass. It's the energy cost of maintaining that specific topological configuration.
The energy of the knot.
Yes. And finally, charge. This emerges from phase discontinuity across torsional folds. Imagine a perfectly smooth surface, right? Then you twist it and create edges or boundaries or folds. These boundaries create a kind of tension or discontinuity in the underlying coherence field, and that's what we perceive as charge. The specific topological geometry of the fold dictates the specific charge value and sign.
So this isn't just theoretical abstraction. This step literally converts that reduced dimensional field into a resonance knot that can no longer propagate as an extended wave. It occupies a discrete phase volume, meaning it's a localized, distinct entity. It's a complete transformation from an extended wave to a discrete localized thing. This is the mechanism by which wave becomes particle, and force carrier potential transforms into matter.
It's a complete transformation, yeah. A profound example of emergence from structure, from topology. The paper even provides a brilliant visualization in its appendix, the boson-fermion reduction cascade diagram.
Oh, a diagram. Let's walk through that. Visuals help.
Definitely. It really brings this abstract process to life. It starts at the very top level with the omnilectic coherence field.
Right, that's the absolute foundational level you mentioned. What does omnilectic mean here?
It's described as the all-encompassing symmetry field that underlies all reality. At this stage, there's no quantization or dimensionality yet. It's just pure, undifferentiated potential, the cosmic canvas before anything is painted on it.
Okay, pure potential. Then the next step down shows the emergence of the bosonic coherence wave. And yeah, it's depicted as a typical wave, like a sine wave extending out.
Right. This represents the first emergence from the field, propagating symmetry, energy, and resonance without individuation or mass. It's the highest symmetry, most extended form, like a pure musical tone resonating throughout the universe, undisturbed.
And then we see the action of the dimensional reduction operator, ROD. It transforms that wave into a phase-confined resonance sheet, which looks, yeah, kind of like a flattened, perhaps donut-shaped surface.
That's the intermediate state. It's described as the intermediate surface upon which coherence is partially constrained. It's still continuous, but its spatial freedom has been significantly reduced. It serves as the substrate for the next step, the chirality induction. Imagine taking that infinitely extending wave and folding it down onto a single plane, or maybe rolling it into a tube or torus. The energy is still there, but is now more concentrated in a defined region.
Got it. And finally, the torsional chirality operator, T-touch, takes that phase sheet and transforms it into the fermionic knot, depicted as, yeah, a knotted, maybe donut-like structure or something like a tangled coil. Looks complicated.
And that's the final structure, a quantized chiral massive particle resulting from torsional locking of reduced coherence. This diagram visually summarizes the entire transformation cascade. Boson, Ord, phase sheet. It emphasizes that fermions emerge not from distinct fundamental fields, but from these modulated reductions of the same bosonic substrate. It's a nested ontological structure, right, rather than a dualistic one. This truly unifies the origins of matter and force, suggesting they are simply different topological expressions of the same underlying coherence. 4. Beyond individual particles. Building complex structures.
Okay, this framework is already challenging our assumptions about individual particles, but what happens when we start building more complex structures? Like, say, protons and neutrons, which we know are made of quarks themselves, fermions. How does this coherence model extend to composite particles? Does it go beyond the individual knots?
That's a really important question, yeah, because the model needs to explain not just the individual building blocks, but how they interact and combine to form stable, larger entities like protons, neutrons, atoms.
Right, the stuff we actually see.
Exactly. The paper does expand this framework. It starts by reiterating that each fermion is a topological coherence knot. Remember, not a point particle.
Not a point, a knot. Got it.
These knots possess their spin from that internal torsion closure, mass from localized phase curvature, and charge from chirality boundary discontinuity. They're essentially stable phase structures that can interact. But crucially, they do so by exchanging coherent resonance via bosonic channels.
So the bosons still play a role in interactions.
Yes, the coherence field doesn't just create them. It also facilitates their communication, their interaction, through these bosonic coherence waves.
So an electron or quark isn't a tiny billiard ball. It's a persistent, stable knot in the coherence field. How do these knots bind together, then, to form something like a proton? We know gluons are involved in that in standard quantum chromodynamics UCD. How does Lillian's model redefine gluons and their role? Does it fit?
Exactly. In conventional QCD, gluons mediate the strong interaction between color-charged quarks. They're often pictured as, little force particles flying back and forth between quarks, holding them together.
The strong force carriers.
Right. But in this coherence model, gluons are radically reinterpreted. They are not force carriers in the classical sense, but coherence routers that dynamically bind multiple fermionic knots through SU3 phase symmetries.
Coherence routers, that's a fascinating term. What do they actually do in this context if they're not just carrying a force? How does an SU3 symmetry act as a router?
Okay, think of it this way. Each gluon is described as a recoherence operator. Their job is to maintain the resonance between fermionic knots, preventing them from decohering, essentially, and enabling what the paper calls coherence entanglement between them.
Maintaining resonance.
Okay, mathematically, you could imagine the gluon operator, let's call it GSU3, taking a set of individual fermionic knots, like the three quarks, F1, F3, Fu3, and transforming them, or rather maintaining them, as a stable baryonic composite knot, KB.
So it's managing the relationship.
Yeah. If each quark is a complex knot in the coherence field, gluons are the intricate dynamic connections that ensure these knots remain synchronized and in tune with each other. They maintain a stable, unified resonance, all while adhering to the SU3 color symmetry rules. They ensure these knots stay synchronized and connected within the coherence field.
So they're not pushing or pulling in the simple sense. They're ensuring that coherence remains between these localized knots, actively maintaining a stable composite resonance structure. That's a fundamentally different way of thinking about the strong force.
There really is.
And then we get to baryons, like protons and neutrons, which are typically seen as three quarks bound by these gluons. How does this model describe them given this new understanding of quarks as knots and gluons as routers?
Baryons are redefined here as triple knot coherence structures. They consist of three fermionic substructures, what we know as quarks, which are stabilized by that SU3, routing from the gluons, and by their own internal phase resonance.
A three-knot system.
Right. The gluons, acting as those coherence routers, maintain dynamic phase-locking conditions between the quark knots. This ensures three crucial things: the conservation of total symmetry, like color neutrality, the quantization of internal torsion, which gives the net spin of the baryon, like spin half for protons and neutrons, and the overall stability of the coherence node configuration. This means the quarks aren't just stuck together passively. They're in a constantly maintained, intricate dance of resonance within the coherence field.
So a proton isn't just three discrete quarks held by gluons. It's a deeply intertwined, dynamically phase-locked system of three coherence knots, all resonating together, managed by these coherence routers. And this has implications for how we understand nuclear structure itself. Does this change our view of how atomic nuclei made of protons and neutrons are built?
Absolutely. This framework suggests that nuclei are not simply assemblies of discrete nucleons, protons, and neutrons, which are themselves composite knots. Instead, nuclei are viewed as nested coherence bundles.
Nested bundles.
Yeah, where the geometry of resonance overlaps and the torsional compatibility between these nucleon knots determines critical properties. This includes things like the nuclear binding energy, how much energy it takes to hold a nucleus together, the decay probability of unstable nuclei, and even transmutation pathways, like how one element might naturally change into another through radioactive decay.
So it's about the geometry of the resonance.
Exactly. This points toward a completely new, coherence-based model of nuclear physics, effectively embedding quantum chromodynamics into a deeper resonance ontology. It implies that the nucleus isn't just a collection of static parts, but a complex interacting system of nested, phase-locked coherence, where stability is fundamentally a function of resonant harmony. V-shaping physics. Broad implications.
Okay, this reinterpretation of particles as coherent structures, rather than, point-like entities, obviously has massive implications for all of physics. It's not just about individual particles, it's about the entire framework we use. Let's start with the Standard Model, which is, our most successful theory of particle physics. How does Lillian's model reimagine it? How does it fundamentally alter our understanding of the very categories we use to classify particles?
Yeah, the implications are huge. The Standard Model classifies particles by their symmetry groups, U1 for electromagnetism, SU2 for the weak force, SU3 for the strong force, and it assigns them intrinsic properties like mass, charge, and spin. Things they just have.
Right, the periodic table of particles almost.
Kind of, yeah. This coherence model reframes all those fundamental concepts. It takes these seemingly intrinsic properties and explains them as emergent phenomena, as consequences of the dynamic structure of the coherence field itself. It's a shift from describing what particles are to understanding how they become what they are.
So the familiar table of particles and their properties gets a complete ontological makeover. Can you walk us through some of those reinterpretations, maybe contrast them directly with the Standard Model's view, property by property?
Certainly. Lillian's work proposes a direct remapping of these core concepts, offering a unified generative origin for them. Host speaker. Okay, let's start with particle types. Expert speaker. In the Standard Model, we have a fixed set of fundamental particles, like distinct species. Here, they're no longer separate species, but topological reductions of a coherence field. This means an electron and a neutrino aren't just different. They are different ways the coherence field has been locally folded and reduced. Different stable knots. Host speaker. Different knots in the same field. Then what about mass? Expert speaker. Conventionally, mass is an intrinsic property, sometimes explained as an interaction with the Higgs field. In this model, mass isn't intrinsic at all. It's the degree of coherence localization, how tightly bound and concentrated the coherence is within a specific topological structure. The more compact or knotted the coherence, the more massive the resulting particle. Host speaker. So heavier particles are just tighter knots. Makes sense. Charge. Expert speaker. This is typically seen as a fundamental property, quantized and inherent. Here, charge becomes boundary chirality in phase torsion, a result of the twisting and folding of the coherence field itself. Imagine that a specific twist or fold in the coherence field creates a boundary that interacts in a particular way, and that interaction manifests as electrical charge. Host speaker. A property of the fold. Okay. Spin. Expert speaker. In the standard model, spin is an intrinsic angular momentum, like a tiny spinning top. In the coherence model, spin is the result of torsional phase locking, derived directly from the internal geometric constraints of the coherence knot. That half-integer spin of fermions, for instance, naturally arises from the specific topological structure that only returns to its original state after 2 full rotations, like we discussed with the Möbius strip analogy. Host speaker. Right. And finally, interactions of forces. Expert speaker. Instead of forces mediated by discrete particles as changing other particles, like photons for EM, interactions become coherence routing and resonance entanglement via gauge symmetries. This means fundamental forces aren't about pushes and pulls in a simple sense, but about the dynamic maintenance and exchange of coherence patterns between particles, facilitated by those bosonic coherence routers or waves we discussed.
Okay, so the key takeaway here is that particles aren't distinct species at all, but rather exist on a continuum of coherence reductions. Bosons and fermions are simply unified as modalities of phase topology. They're all expressions of the same underlying field, just in different states of coherence and structural complexity.
Exactly.
That truly unifies the origins of matter and force, which, wow, raises a very big question about one of the most sought-after theories in modern physics, supersymmetry, or CZUI.
Indeed. Supersymmetry is a huge concept in modern physics, a very elegant mathematical idea. It posits a fundamental boson-fermion partnership, where every known particle has a hypothetical superpartner with a different spin.
So every fermion has a boson partner, every boson has a fermion partner.
Right. It attempts to unify forces, solve problems like dark matter, fix the hierarchy problem. A lot of potential benefits. The Large Hadron Collider has been searching intensely for these hypothesized superpartners for years, but so far, well, nothing definitive has shown up.
And this is where Lillian's model offers a truly radical proposal, isn't it? If bosons and fermions are just different phase states of the same underlying coherence, what happens to the whole idea of needing separate superpartners?
This is honestly one of the most profound implications of this coherence model. If the fundamental distinction between bosons and fermions dissolves, because they are simply coherence phase states, different topological transformations of the same field, then the paper suggests supersymmetry becomes structural, not particle dualistic.
Structural, not particle dualistic. What does that mean?
It implies that each fermion already contains its bosonic ancestry within its reduction lineage and vice versa. They are inherently linked through the transformation process itself. So the surprising implication is that superpartners need not be new, undiscovered particles at all.
No new particles.
Instead, they could potentially be coherence reversals or unwrappings, occurring under different phase conditions or energy levels.
Wow. So the reason we haven't observed superpartners might not be that our colliders aren't powerful enough, but that we've been looking for them in the wrong way. They're not distinct new particles, but maybe just different phase states or structural modes of the particles we already know, perhaps hidden within intricate reduction or re-extension pathways, a kind of inherent duality within the particles themselves.
It's a possibility raised by this framework. It would mean supersymmetry is an inherent property of the coherence field structure, not something that requires doubling the entire particle zoo.
That would certainly explain the lack of experimental evidence so far. It's a profound reevaluation of what supersymmetry fundamentally represents. And this extends to quantum field theory, QFT itself, right? Which is the bedrock of modern particle physics, modeling particles as quantized excitations of abstract fields. How does this coherence framework offer a deeper view of QFT?
QFT has been incredibly successful, undeniably. But it also has its challenges, like the problem of infinities that require complex mathematical fixes called renormalization techniques.
Right, sweeping infinities under the rug, some might say.
Well, it works, but it feels a bit like patching things up. This coherence framework suggests that fields themselves are modulations of the underlying coherence field, not fundamental objects in their own right. They are more like emergent patterns or ripples on the deeper ocean of coherence.
So the fields aren't the bottom layer.
Maybe not. Lagrangians, which are the mathematical descriptions used in QFT to describe the dynamics of quantum fields, are reinterpreted here as projected operators that describe local reductions of this coherence. Even vacuum fluctuations, a constant, seemingly random activity in what we call empty space, are potentially not just random noise, but microcoherence instabilities around the threshold of reduction. The field constantly testing its boundaries may be on the verge of creating new structures.
So QFT, while powerful, is like a simplified, perhaps low-resolution statistical picture of a much more intricate reality. It's an effective theory, but maybe not the ultimate one.
Precisely. QFT could be seen as a low-dimensional statistical approximation of a much richer coherence dynamics. This naturally opens the door for non-perturbative models, moving beyond the complex renormalization techniques of QFT toward a true structural unification based on coherence. It suggests a path to a more complete and perhaps more elegant theory, one that doesn't just describe phenomena but explains their very origin from first principles.
That's a huge shift. And what about the predictive and unificatory power of this model more broadly? Does it naturally explain things that have been persistent puzzles in physics, going even beyond the standard model?
Yes. The claim is that by rooting particle properties in coherence dynamics, the model naturally explains several fundamental aspects, offering potential solutions to long-standing enigmas. Host speaker. Like the mass hierarchy. Why particles have such wildly different masses? Expert speaker. Exactly. The widely varying mass values among particles emerge naturally via reduction depth. How intensely localized the coherence is. More severe reductions or tighter knots simply result in more mass. It's a direct consequence of the topology. Host speaker. Okay, what about gauge symmetries? Those U1, SU2, SU3 rules. Expert speaker. These aren't arbitrary rules imposed on the theory, but are understood as stable coherence routing protocols that maintain the integrity and interaction pathways of these phase structures. They are the rules of the coherence dance, host speaker, and the Higgs mechanism, the thing that supposedly gives particles mass, expert speaker. This, which gives particles mass in the standard model by their interaction with the universal Higgs field, may be replaced or reinterpreted by torsional coherence entrapment itself. In Lillian's model, remember, mass is not acquired by interaction with an external field, but is the internal, localized energy of the particle's own topological structure. Host speaker, so no Higgs field needed. Expert speaker. Potentially. Instead of being slowed down by an external field, a particle is mass because it is a self-contained, localized energy node. This offers a more intrinsic, topological explanation for mass, potentially unifying it with other particle properties that arise from these coherence transformations. Host speaker. And gravity, the elephant in the room for particle physics. Expert speaker. And though the paper indicates more work is needed here, gravity itself is framed conceptually as a large-scale coherence curvature effect, suggesting it's not a separate force mediated by gravitons perhaps, but a macroscopic manifestation of the geometry and dynamics of the underlying coherence field itself.
That's incredibly ambitious. It sounds like this redefinition transcends fragmentation and proposes a resonant unity of all physical phenomena. It's not just about unifying forces, it's about unifying the very nature of existence, from particles to space-time itself. 6, the photon-electron duality, a coherence perspective. Now, let's zoom in on one of the most intriguing aspects of this theory, one that truly reshapes how we view fundamental particles. The relationship between the photon and the electron. I mean, in the standard model, they are ontologically distinct, one a massless force carrier, the other a massive matter particle. Chalk and cheese almost.
Absolutely, they seem fundamentally different.
But in this coherence framework, they're not just connected, they're fundamentally two sides of the same coin, right? Different manifestations of the same underlying reality.
This is a classic conceptual puzzle in physics, how light relates to matter. And the coherence framework offers a truly elegant potential solution. First, photons are understood as unbound propagating coherence waves.
The pure waveform.
Exactly. And their properties are a direct consequence of this fundamental nature. They have no mass. Because their coherence is fully extended, unlocalized, they are pure, unconstrained waves of the coherence field. They have spin 1, arising from their extended phase rotation across spatial dimensions, a complete harmonious rotation. They have no charge, because there's no chirality entrapment or boundary locking, no internal twists or folds to create that localized charge effect, and they travel at a constant speed. They propagate at the maximal coherence transmission rate, which is the speed of light, because they are the purest, most efficient form of coherence propagation.
Okay, so a photon is the purest expression of an unfettered coherence wave, a bridge of resonance, a perfect ripple in that cosmic ocean. But then how does that pure massless wave transform into an electron, a particle with mass, charge, and that weird half-integer spin? This is where the magic, or rather the profound physics, happens, isn't it?
Indeed. This is where the core insight of dimensional reduction and torsional chirality locking comes into full play. The paper proposes that electrons arise directly from the dimensional contraction and torsional locking of the photon's coherence wave.
From the photon itself.
Yes. Diagrammatically, it's expressed simply as photon ard plus teach, electron. The very operators we discussed earlier, ard and teach, are precisely what bridge this seemingly vast divide between light and matter.
This is the profound conceptual leap. The electron is literally a transformed photon. The paper even says something like, the electron is a photon in a locked state, a standing wave confined within a coherence trap. That's a complete game changer for how we perceive reality and the fundamental building blocks of matter.
It really is. This transition embeds the photon's field into a confined toroidal knot. And that very act of confinement is what gives rise to all the familiar properties of the electron. Host speaker. So mass emerges, expert speaker, emerges from resonance localization within that knot. The very act of trapping the photon's extended coherence into a localized stable structure gives it mass. It's like a localized self-sustaining energy vortex. Oh, speaker. Okay. And spin, expert speaker, results from two-chirality torsion within the electron structure. That specific inherent twist within its topological form necessitates the half-integer spin, this 720-degree rotation symmetry. Host speaker. And charge, expert speaker, arises from topological phase boundary created by the locked structure. The way the coherence wave folds and self-intersects creates a persistent boundary condition, which manifests as electrical charge.
So the electron isn't just like a photon in some ways. It fundamentally is a photon, just in a different, highly structured, locked state. It truly is a mind-bending shift, isn't it? The idea that what we perceive as solid matter is just a tightly wound knot of energy that was once a free-flowing wave. It almost redefines what we mean by particle altogether.
It certainly challenges the notion of fundamental, irreducible points.
It makes you wonder how much more of reality is just a symphony of these subtle coherence states that we're only just beginning to maybe decipher. This also has implications for understanding the electron cloud around an atom, right? Traditionally, we model it as a probabilistic wave function, a fuzzy region where the electron is likely to be found.
That's right. In this coherence model, the electron cloud is reframed. It's seen not as a static probability distribution, but as a dynamic coherence halo.
A coherence halo.
Yeah. This halo is composed of persistent photon-like coherence modulations orbiting the fermionic core, the central knot, and involves the exchange of microcoherent excitations within its stable torsional boundaries. It's seen more as a resonant field zone rather than a stochastic shell.
So it's active, not just probable.
Exactly. When external photons interact with this field, they're either absorbed, causing transitions between the electron's allowed coherence states, what we see as energy levels, or they stimulate resonance realignment within the electron structure, leading to scattering.
This naturally accounts for phenomena like absorption spectra, where electrons jump energy levels by absorbing specific photons, or the photoelectric effect, where photons knock electrons out. It also seems to fit with virtual photon exchange in quantum electrodynamics, QED, where particles interact by exchanging these virtual photons. It all fits within this single coherence field model.
That's the claim. It's all about resonance and coherence patterns, rather than discrete particles firing at each other across empty space.
Okay, and it also provides a natural explanation for phenomena like electron-positron pair creation from high-energy photons, or their annihilation back into photons. These are fundamental processes in high-energy physics. How does that work here?
Well, if they're not fundamentally distinct particles, how does creation-annihilation work?
Yeah.
In this framework, pair creation is when a high-energy photon undergoes chirality bifurcation and torsional stabilization. Essentially, its coherence splits and locks into two complementary topological knots, an electron and a positron. They are distinct but complementary structures formed from the same initial wave.
Bifurcation, like a fork in the road for the coherence.
Something like that.
Yeah.
And annihilation is simply the reverse process. The coherence knots unwrap, re-extending into free photon waves. The knots untie, releasing their localized energy back into propagating coherence. It's not about particles appearing and disappearing from nothing. It's about the coherence field changing its state of localization and expansion, undergoing a kind of topological phase transition.
Okay, so to summarize this identity by reduction, we can compare the photon and electron directly, almost like, two sides of the same coin, as you said. They are fundamentally the same underlying coherence, just in different states of topological organization.
We absolutely can.
Yeah.
If we look at their key features side by side, the reinterpretation becomes crystal clear. Mass. Photon has none. Fully extended coherence. Electron's mass arises from the energy concentrated by its coherence lock, its internal knot. Spin. Photon has spin 1, extended unconstrained rotation. Electron has spin
From its torsional chirality, needing 2 turns to realign. Charge. Photon is neutral, no boundary. Electron's charge emerges from a phase fold, a topological boundary condition. Structure. Photon is an open coherence wave, a pure ripple. Electron is a closed resonance knot, a self-sustaining vortex. Role. Photon is a mediator of coherence, carrying information and symmetry. Electron is a carrier of Lock's coherence, forming stable matter.
This perspective truly restores a kind of unity, doesn't it? Showing quantum entities as phase states of a singular field, governed not by discrete particle classes, but by the geometry and topology of coherence modulation. It's a deeply satisfying and elegant concept, suggesting a profound simplicity beneath the apparent complexity of the universe we observe. 7. Experimental predictions and the future of physics. Okay, this model is incredibly ambitious, offering a complete reinterpretation of fundamental physics. But for any scientific theory to be taken seriously, it needs to be testable, right? It can't just be a nice story. Does this coherence ontology offer falsifiable predictions that could actually be observed in experiments and potentially overturn our current understanding?
It absolutely does, and that's crucial. This model isn't just theoretical speculation. It proposes unique physical behaviors that diverge significantly from the standard model and, crucially, may be testable with current or emerging technology. Lillian outlines 3 key observable predictions in the paper, each of which, if observed, would provide strong evidence for the existence of this underlying coherence field and its transformational dynamics.
Okay, I'm intrigued. What's the first prediction and how would it manifest? What would we look for?
Prediction 1. Coherence-based mass modulation. The model suggests that electrons or other fermions, when subjected to extreme torsional perturbation, for example by intense, precisely tuned laser-induced coherence fields, might exhibit reversible mass modulation.
Reversible mass modulation, you mean changing a particle's mass?
Yes, temporarily. This is profound because it implies that a particle's mass isn't a fixed constant, but could be dynamically altered based on the integrity and the induced stress on its internal coherence field structure. Imagine being able to slightly change the effective mass of an electron just by shining a very specific type of intense light on it, and then having it return to its original mass once the perturbation stops.
Oh.
This isn't just about adding kinetic energy, it's about potentially deforming the internal structure of the coherence knot itself.
Yeah.
We'd be looking for tiny transient shifts in a particle's inertial or gravitational mass under these extreme conditions.
That will be revolutionary, truly. It would literally mean we could untie or retie the coherence knot that gives a particle its mass, even just slightly. Okay, what's prediction number 2?
Prediction 2. Photon coherence disruption yields fermion signatures. This one is equally exciting, maybe even more dramatic. It suggests that high-intensity coherent photon pulses near critical energy thresholds may self-collapse into particle-antiparticle pairs without traditional mediators.
Self-collapse. Photons turning into matter on their own.
Potentially. In standard physics, you usually need specific interactions or very high-energy collisions, often involving a vacuum fluctuation or interaction with another particle's field, to generate matter from energy, like in pair production near a nucleus. Here, the theory posits that the photon itself, if its internal coherence is sufficiently stressed or forced to fold by extreme intensity, can directly transform into matter-antimatter pairs. This depends not on collision, but on resonance, folding within coherence zones of the photons themselves. The photons literally fold themselves into matter.
So, a powerful enough laser beam under the right conditions could spontaneously generate electron-positron pairs, maybe even quark-antiquark pairs, without needing to crash into anything, just from the intensity of the light itself. That would be an undeniable signature, a direct observation of energy transforming into matter through this coherence mechanism. Okay, and the third prediction.
Prediction 3. Fermion recoherence leads to ZPE-like radiation. This prediction looks at the inverse process, matter turning back into pure coherence. It posits that highly compressed fermions, such as those found in the extreme conditions inside neutron stars, or perhaps even hypothetically within future coherence engines, devices designed to manipulate this field, might unwind into high-frequency coherent radiation.
Unwind, like the knots untying.
Exactly. This radiation would resemble pure photon emission from coherence reservoirs, potentially reminiscent of zero-point energy radiation concepts. Essentially, if you could force these coherence knots to untie under extreme pressure or specific field conditions, they would release their trapped structural energy back as highly coherent light. You would be turning matter back into pure energy, but not through standard annihilation with antimatter, rather through a structural unraveling.
These are incredible claims, suggesting entirely new ways to maybe generate energy or even manipulate matter at its most fundamental level someday. But where exactly could we test these radical ideas? What are the experimental access points, the real-world laboratories or setups where we might actually see these effects? Are they feasible?
The paper points to several cutting-edge facilities and concepts that are either already in operation or are on the horizon, making these tests potentially feasible, though certainly challenging. 1. Host speaker. Like where? Expert speaker. First, ultra-high-intensity lasers. Facilities like the Extreme Light Infrastructure, ELI, in Europe, and upgrades at places like SLAC National Accelerator Laboratory can reach photon energies and intensities approaching the thresholds where such coherent breakdown, mass modulation, or self-collapse might occur. Scientists would need to look for very subtle, unexpected phenomena in the data, maybe torsional phase slips in electron behavior under intense fields, or delayed recombination events after pair production, or those unexpected pair generation events we just discussed, which would defy explanations from current quantum electrodynamics. It would involve meticulously monitoring high-energy photon interactions for signs of internal structural change. 2. Host speaker. Okay, so high-power lasers are key. What else? Expert speaker. Second, quantum vacuum modulation chambers. Modified Casimir cavities, or dynamic boundary. Quantum electrodynamics, QED systems, could be used to specifically test for photon fermion coherence folding, or even exotic phase entrapments under highly controlled conditions. By manipulating the boundaries of the quantum vacuum very precisely, one might be able to create conditions that encourage these coherence transformations at much lower energies than brute force collisions. 3. Host speaker. Manipulating the vacuum itself. Interesting. Any others? Expert speaker. Third, electron coherence mapping. Advanced interferometric measurements of electron phase halos, the fields around electrons, could potentially reveal structure beyond probabilistic shells, meaning direct evidence of coherence resonance fields within the electron, rather than just seeing it as a fuzzy probability cloud. If the electron truly is a coherence knot, that ultra-precise measurements of its surrounding field might reveal internal, stable patterns of resonance that aren't predicted by current point particle models. 4. Host speaker. Looking for structure inside the electron cloud. And fourth, expert speaker. Fourth, supercoherent crystalline structures. New materials designed to preserve long-range phase alignment, like maybe high-temperature or even room-temperature superconductors, if we find them, might serve as amplifiers or traps for observing these elusive microcoherence effects. These materials could potentially host and manipulate these coherence phenomena on a larger, more observable scale, acting almost like macroscopic testbeds for the theory.
These are real, tangible experiments that could, in principle, either validate or falsify this entire framework. That's the hallmark of a truly scientific theory, right? The ability to make specific, testable predictions that challenge existing paradigms. Beyond these direct predictions, what are the broader theoretical implications for unification and the future of physics? How might this reframe the very landscape of scientific inquiry if it turns out to be right?
Well, if validated, this coherence ontology offers a potentially profound bridge between seemingly disparate fields of physics, connecting them through a single, unified underlying principle. Quantum physics is explained naturally through torsional quantization, where fundamental properties like spin and charge arise directly from the geometry and topology of twisted coherence. Relativity. A large-scale coherence curvature might explain gravity, suggesting that the warping of space-time isn't fundamental, but is itself a manifestation of the underlying coherence field's geometry. Thermodynamics. Entropy, often seen as a measure of disorder, could potentially be understood as a consequence of coherence loss or decoherence within the system, a move away from perfect resonance. Even consciousness and information. While much more speculative, the paper hints at them as potentially being coherent sensitive domains, suggesting that the very fabric of reality, including information processing and perhaps even consciousness, might be deeply linked to the integrity and dynamics of coherence.
Wow. So it's not just aiming for a grand unified theory of particles and forces, but potentially a genuine theory of everything, connecting the very small to the very large, and maybe even to the nature of mind and information itself. That's ambitious.
Extremely ambitious. But it notably supports a field-unified theory without requiring exotic extra dimensions, which is a common feature and complication in other unification approaches like string theory. Instead, it works within our known dimensions but fundamentally redefines them. It proposes a radical redefinition of spacetime as coherence geometry, which is a truly monumental idea. And it provides a natural basis for resolving long-standing puzzles like the mass hierarchy, the quantization of charge, and the chirality of spin things, which are often simply taken as given as input parameters in current models. This suggests a new research paradigm altogether.
It sounds like a fundamental shift in scientific focus, moving away from merely dissecting the universe into smaller and smaller pieces, and towards understanding the grand symphony of reality, the relationships, the resonances.
It is. This model opens the door to coherence physics as a foundational discipline. It restores the unity between particle and wave in a novel way, treats dimensionality itself as emergent, and builds from generative phase dynamics rather than static particles. It suggests that the next era of physics won't be about finding ever smaller, more fundamental point particles, but perhaps about revealing the deeper harmonics of coherence from which all phenomena emerge. It's a shift from dissection to understanding the symphony of reality, where the universe reveals itself as an intricate, self-organizing pattern of pure resonance. Outro.
Okay, let's try to unpack this just one final time and truly appreciate the sheer scope of this reinterpretation we've been exploring. We've journeyed from the conventional understanding of particles, bosons, and fermions as fundamentally distinct entities to a universe potentially woven from a foundational coherence field. Yeah, a single underlying substrate.
We've seen how bosons can be viewed as extended waves, like pure ripples of coherence, and fermions as coherence knots formed through these intricate dimensional and torsional reductions of those very waves. We've explored the precise mechanics of this transformation, supposedly driven by the dimensional reduction operator and the torsional chirality operator, which sculpt extended coherence into localized, massive chiral entities like electrons.
And perhaps most mind-bendingly, we've seen how this framework reinterprets everything from gluons binding quarks acting as coherence routers to the profound electron-photon relationship, suggesting the electron is simply a photon in a locked state. A standing wave of pure energy that has somehow curled in on itself to become what we perceive as matter.
The profound realization here, if this model holds any water, is that the universe might not be made of hard, discrete particles at all, fundamentally, but rather nested, self-resonant coherence structures, vortices of phase and torsion wrapped within a higher field.
It's a universe of music, not just building blocks. Every particle is a unique chord, maybe, a specific rhythm in a vast cosmic symphony. This isn't just a reclassification, it's a potential recomposition of reality itself.
And the model suggests, perhaps provocatively, that coherence links physics and consciousness, that coherence embeds order within apparent chaos, and coherence rescues unity from fragmentation. It offers a vision where everything is interconnected at its deepest level, bound by an underlying universal harmony or resonance.
So the final thought for you, the listener. What does it mean for you if the deepest reality is not about fundamental, irreducible particles, but about the music of coherence? How might this reframe your own understanding of connection, of information, of the very fabric of existence, knowing that potentially everything, from the light that touches your eyes to the very matter that makes you, is a manifestation of this profound underlying coherence?
It's certainly something to ponder.
It's a call, perhaps, to reawaken physics, not just as calculation, but as a resonant exploration of the real, where the universe is a symphony waiting to be fully heard, and perhaps even understood as an intricate dance of cosmic harmony.
The beauty of a deep dive like this, exploring such a radical idea, is that it doesn't just give you answers. It really opens up entirely new questions and provides a completely new lens through which to view the universe, inviting further exploration and thought.
Keep exploring, keep questioning, and keep diving deep into the fascinating and possibly resonant coherence of reality.